In this video, we'll look at different ways that we can display quantitative data. To look at the distribution of quantitative data, what we're looking for is we look for an overall pattern in a graph and then deviations from the overall pattern. So when looking at the overall pattern, we'll look at the shape of the data, the center of the data, and the spread of the data. And then outliers are deviations from that overall pattern. So there are three different ways that we can talk about the shape of data. Data can be symmetric. It can be asymmetric, either left skewed or right skewed. And then we talk about something called unimodal or bimodal. So unimodal, it's going to have one peak to it. So something like, something like this, where you have one peak, that would be unimodal. If you had two peaks, that would be bimodal. So here's some symmetric shapes. This is a symmetric bell shape. Symmetric means that if you drew a line down the middle of it, like this, it's mirror image, same both sides. Bell-shaped symmetric distributions are something you will get very used to as you study statistics. We could also have something that's mound-shaped and symmetric. Again, if you drew that line down the middle, mirror image. You can have something called a uniform distribution. Every single value has the same frequency. Now this is an example of an asymmetric distribution. And so we call those skewed. If you drew a line down the middle, it would not be a mirror image. And it's skewed to whatever direction the tail is at. So this is called skewed to the left because the tail runs out to the left. And here's skewed to the right because on this one we have the tail going out to the right. Now, outliers are extreme values that fall outside the overall pattern. And we will talk, when we go a little bit further, about ways to actually calculate outliers, which ones are outliers and are not. You have to remember that outliers can occur naturally, or you can have them in your data because of errors, either in recording or of measuring or using different units. Histograms are the first way of displaying data that we're going to discuss. And so you want to use those for quantitative variables that can take many values. And you're going to divide the possible values into what we call class intervals. We're only going to deal with the ones that are equal width, although they can be done with non-equal widths. And you count how many observations fall into each interval. So this is analogous to doing age ranges. You know, when you fill out a survey and you have to check what age range you fall into? Those age ranges would be class intervals. And then we'll draw a picture representing the distribution and look similar to a bar graph, but there are some distinctions that we need to discuss. So first of all, you have to figure out how many intervals. So one rule is you're going to calculate the square root of the sample size and round up. And then the size of the intervals, you take your range of the data, which is the max minus the minimum, and you'll divide that by the number of intervals you want. So if you have a range of data that's 100 and you want 10 intervals, each interval would be a size 10. And then you want to make sure that you don't have any overlap in your intervals, and we'll talk about that when we look at one done for us. So here's a case study. We're using weight data from an introductory statistics class. So here's the data. They had, I don't know if they weighed people or just had people self-report their weights, but this is the weight data from that introductory statistics class. One observation per student. So we want to display this data on a histogram. So the first thing we're going to do is we're going to make different classes, different class intervals. And the way we're going to figure out how many intervals we want, we're going to take the number of observations, which is 53. We'll take its square root, which is about 7.2. So we round up, and we get 8. Now our range of data, the largest, the highest weight was 260. The lowest weight was 100. So that's a range of 160. You divide that by 8, and that tells you that your class widths need to be 20. Now I said that we're going to talk about not overlapping. This is what I mean by not overlapping. The first weight group goes from 100 up to, but not including 120, because 120 is included in the next one. The next one goes from 120 up to, but not including 140, because 140 ends up in the next one. You want to be very careful about that, because if you don't do that, you don't know if somebody has a weight that's right at the edge, which group to put it in. Okay, and then what you do is you do a bar that goes up to the frequency. So there were 7 students whose weight was greater than 100 or greater and less than 120. There were 12 students whose weights were between 120 and 140, but not including 140. So see, I told you this would look kind of like a bar graph, but a couple things to note. That this is numerical, this is quantitative data, not qualitative. So on a bar graph, you would have the qualitative variable on one of the axes. And the second thing to notice is we don't have distinctions. The bars aren't distinct from each other. They don't have gaps between them. Okay? They're smushed all up together. Second way we're going to display quantitative data are what's called stem and leaf plots. And we'll separate each observation into the first part of the number, which we call the stem, and the second part of the number, which we call the leaf. And we're going to write those in columns with a line between them. Okay, so it's easier to just see what this looks like. So again, we have our weight data, and the stems are going to be the first part of the number. And in this case, it's going to be the tens. So the hundreds and tens column are going to form together the stem. So there'll be a line that comes down here between each stem and its leaf. Okay, I'm just separating out the stems and the leaves for you here. Then we'll put them all together onto a separate stem and leaf plot. And I'll show you how to do these first 3 onto the stem and leaf plot. So we'll take, let me get this to move down for me just a little bit. Cut off the top number. That should be a 10 up at the top. Okay. So 192 is our first observation. So we'll take the 19, because the first part of that number is 19, and we'll write a 2 after the 19. 152, we go up to the 15 and we put a 2 there. 135, we go up to the 13 and we put a 5 there. Now what if my next weight was 194? I go to the 19 and right next to the 2 I would write a 4. So that 2 and that 4 on that line One of them represents a weight of 192. The second one represents a weight of 194. So for each digit you have to the right of the line represents a separate data point in your data set. And this, you can see the whole thing put together. Again, the 10s are cut off, but you can see the 11s onward, all put together. And I encourage you to compare this to the histogram of the same data so that you can see how they look so similar to each other and where they're not similar to each other, and make note of those similarities and differences. Okay, extended stem and leaf plots is just when you cover a very small range of values. To get a better picture, you want to do what's called splitting the stems. So instead of having one line that's 15, you would have two lines that are 15. And on those two lines, we'll just take this part over here. On the top, you would have 150 to 154 will be represented by that top stem, and values from 155 to 159 will be represented on the bottom stem. The last thing we want to talk about with displaying quantitative data is time plots. And a time plot is going to show behavior over time, with time always being on the horizontal axis and the variable you measure always being on the vertical axis. And you're looking for trends and deviations. And sometimes if you connect data points by a line, even if there's no data between those, just connecting them can kind of show you those trends, emphasize it. There are also patterns that repeat seasonally or yearly or weekly, depending on what kind of data you're looking at. So you're looking for those kinds of patterns as well as the overall pattern. The stock market is a really good example of something that you would look at a time plot to understand. So here's something that, that somebody made a time plot for. Time is on the horizontal axis. It's years of fall semester. So fall semester 1985 through fall semester 1993. The percent of the class that are freshmen. So you can see that over time it went up, then it came down and leveled off, and then it went back up. And the last one we want to look at, sorry that this cuts off us a little bit, is average tuition of a public school versus a private school. So that's what it says up there, average tuition, public versus private. Okay? And this is two time plots on the same graph so that you can compare them. And you can see that both public and private school tuition went up, but private school tuition went up faster. The increases are greater in the private school tuition. Those are the kinds of trends that you will see in a time plot.